Welcome back, everyone. So in our last video, we really worked on defining different terms for the energy that we can use to describe systems. And so we had the internal energy, the enthalpy, the Gibbs free energy, and the Helmholtz free energy. And we showed how those were just definitions of the internal energy with using different variables. In order to ever be able to define what is the Gibbs free energy of the system or the Helmholtz free energy of the system, we are going to have to define our system. And to do that, one way to do that is that we can give a big explanation of how we set up the experiment. But it turns out that thermodynamics likes to create some concise language around what type of system are we considering. And so in this video, I hope to just explain some of this language and make sure that we are all on the same page as we move to understanding what system we are working with. Okay, so these are the terms and their definitions that we defined in the last video. And so we have the internal energy, the enthalpy, the Helmholtz free energy, and the Gibbs free energy. And remember that these are different definitions of energy, the differences being that we are looking at differences between the variables that the energy is dependent upon. So in all of our talk, all semester, we have been ignoring time. And we're going to continue to ignore time. And we're going to justify our ignoring of time by defining our systems as quasi-static systems. So what do I mean? The state of the system changes all the time. Remember, we were talking about our atoms in our box moving around based upon temperature, having this energy of translations, rotations, and vibrations. And so with this, how can we measure any thermodynamic properties of the system if the thermodynamic properties are defined of the system and not of one configuration of the system? It turns out that we are going to make an approximation, and we're going to assume that our equilibrium of states does not depend upon time. And so this means that if we let enough time go on, we would always see the same sort of average of states. So that means that all measurements are going to occur after the system has had time to reach equilibrium. And so this means that while the system can be changing, that the properties that we are measuring are not. For now, we are not going to study systems unless they are at equilibrium. So, if each of our thermodynamic properties depend upon two variables, this means that the conjugate variables will have to remain constant. So, if we think that G, Gibbs free energy, is a function of temperature, pressure, and number of moles, this means that the conjugates S, V, and mu are going to have to stay constant. So we are going to have fancy words for the things that we are going to hold constant, allowing us to measure a measure of the energy or other parameter of the system based upon what is not moving. Okay, so here we go. Vocabulary. Isothermal systems are constant T, temperature. Isobaric systems are constant pressure. Isochoric are constant volume. Isoentropic, constant entropy. Isoenergetic, constant energy. And then the last one is adiabatic. And this means that no heat is allowed to move. And we haven't talked much about heat yet, but we are working our way to defining what is heat and how heat relates to the energy of the system. So those are the terms for keeping things constant. Some more vocab. An open system. This is a system that can exchange mass and energy with the surroundings. So a beaker on a lab bench. I always think of open as no top. A closed system is a system that cannot exchange mass and does not undergo any reactions. And so this would be like a sealed container of water. A pure system is a system only containing one thing. That can be an element, a molecule, whatever. An isolated system means that no mass or energy is exchanged with the surroundings. A homogeneous system is a system consisting of one phase of matter, so a beaker containing water. A heterogeneous system is more than one phase of matter, so a beaker containing ice and water. Now, it is very possible that a system can be homogeneous, isolated, and closed, and pure. So systems can have any combination of these. Now, there are some that are opposites, like an open system and a closed system, and a homogeneous system and a heterogeneous system. And so something cannot be both homogeneous and heterogeneous. Okay, so I hope this gives us some language to use as we move into more of thermodynamics. In our next set of videos, we are going to start talking about something known as heat capacity. And we will use heat capacity to move into what is the first law of thermodynamics.